All right, hi everyone. We're going to continue with some Lewis structures, and what we're going to do is these examples and talk about exceptions to the octet rule. Okay, and in doing that, then we're going to use and discuss formal charges. So uh, anyway, I've already given away the punchline, exceptions to the octet rule, but if you would, pause the video and try to draw the Lewis structure for ICl5. The first atom is the central atom, and all the chlorines are connected to iodine. So pause the video and draw that. All right, did you run into some trouble? Maybe, maybe not, but you definitely you couldn't follow the octet rule and do this, could you? So let's go ahead and go through it step by step. Let's count the valence electrons. Iodine's in group 7, so it has 7 valence electrons. There's 5 chlorines. Chlorine's also in group 7, so that's 5 times 7 electrons. And so how many do we have? 35 and 7, 42 electrons. That's a lot of electrons, isn't it? And we're going to just call that 21 pairs. And so we're going to stick iodine in the middle, and the other atoms go around it connected by a single bond, because that's the next step. So I'll stick chlorine there, chlorine there, chlorine there, and that's 5. Well, look at that. Already, what does iodine have in its valence shell showing? Each dash, remember, is a bond. That's 2 electrons in that bond. So it has 2, 4, 6, 8, 10. Iodine already has 10 electrons. There's no choice but to exceed the octet rule. So no choice but to exceed the octet rule for iodine, right? Got to have those bonds there. All right, and then let's go ahead and stick the rest of the pairs of electrons around there. So 21 pairs, and I'm just, instead of dots, I'm going to use dashes for the lone pairs this time. It's just a little quicker. So 21 pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, why did I just put 3 more pairs around each chlorine? This I can draw this much nicer on the board. Sorry if that's a little sloppy looking. Um, because each chlorine then has 2, 4, 6, 8. We've filled the octet rule for each chlorine. But did you notice something when I counted? We've only used 20 pairs. We have another pair. We've got a lot of electrons to stick onto the structure, a lot of electrons in the valence shell. Where should that pair of electrons go? Well, it's going to go on the central atom. Why would that be? Well, iodine is bigger than chlorine. It's the central atom. Putting them there is the most symmetric way to do it, right? If we picked out one particular chlorine, why that one and not the others? And so iodine's a lot bigger. It has larger orbitals, more space around it. It can handle that lone pair. And so that's the Lewis structure for ICl5. And here's the deal. Some people think you shouldn't use, there is no octet rule, shouldn't go by. I'm not that far. I don't think that's useful. But we can exceed the octet for a lot of a lot of atoms for any element below, where's my periodic table here so I can show you. So this first row, carbon, nitrogen, oxygen, fluorine, those are the only ones that absolutely have to follow the octet rule. So all of these ones can, if they have to, exceed the octet rule, everything below there. So third row and below. So for the third row and below. So maybe make another little note. Only carbon, nitrogen, oxygen, and fluorine strictly follow the octet rule. And so, yeah, I think some people say, well, why have that rule? It's a good starting point. It's always a good, if you can follow the octet rule and have reasonable formal charges, which we'll talk about in a minute, that's definitely your best structure. So that's where we'll start. So you can expand the octet for elements that are bigger that go below that. Let's do another example though, because I had this example here. So we did that one already. Let's do BH3. Okay, and I think I got enough room on this. So BH3. Draw the Lewis structure for that, and then come back if you would. All right, are you done? So I'm picking extreme examples to force us to not follow the octet rule, right? So when we count this up, well, boron has how many valence electrons? It's in group 3, has 3 valence electrons. Then we have 3 hydrogens, so that's 3 times 1. And so there's only 6 electrons in this molecule, which is 3 pairs. And then if we stick the first element in the middle and connect the other ones with single bonds, we've used up all the electrons, haven't we? All the valence electrons are used, and that's done, okay? And so boron can be electron deficient. It's really small. It's in group 3. It's happy right now. Too much anthropomorphizing. And so boron and beryllium, that actually can form some covalent molecules too, can be electron deficient. That means less than the octet rule. Okay? And so again, only the octet rule is only strictly followed for carbon, nitrogen, oxygen, and fluorine. Let's talk about formal charges then. Can't get the hair off. Need to work out. Haha. Okay, formal charges. So there aren't charges in covalent molecules. Formal charges is bookkeeping for charge. It's a formality. So it's sort of like oxidation numbers, right? We're just keeping track of the electrons of the charge. They're not real. And so what you're going to do is compare, or I'm going to write this out and talk about it, I guess. So consider first the number of valence electrons in a neutral atom. And then in your structure, you compare how many valence electrons are on that atom in its valence shell versus how many it would have if it was the neutral atom. So how many valence electrons are on the atom in the molecule? Now how do we count those? So this is really important. And your book has like a mathematical formula for that. I don't think you're going to need I hope you won't need a mathematical formula. We don't want to make it any harder than it is. If you sort of understand it, hopefully it'll be easier to remember. So how do we count those valence electrons for each atom in the molecule? Well, if there's a lone pair, So lone pairs, does it make sense that those count fully for that atom? Whatever atom they're on. I mean, they're lone pairs. They're completely on that atom. So a lone pair is 2 electrons on that atom. Now, what about bonding pairs? Does it make sense to you that they should count half? So when we're fulfilling the octet rule, we said they can count in both places to fill the valence shell. But when we're counting charges, which aren't charges, but formality of charges, formal charges, we have to split them back up because the nucleus charge, right? And so we have to split those back up. So bonding pairs count half. So we'll say we'll split between the atoms in the bond, which really just means they count half. And in fact, I think when you count them up, that you can just count them in a certain, I'll show you when we do an example when you're counting. So let's go back and look at our BH3, right? So the shared ones, we're going to count half. All right, so let's look at BH3 again. Boron here and hydrogens around it. And looking at, let's do the hydrogens, right? So hydrogen has 1 valence electron, right? A neutral atom, so a hydrogen atom, 1 valence electron. And then the bond, we're counting it as half, so half of 2 electrons. So half of 2 electrons, and again, I don't think you need to do the math here, is 1 electron. And so what that means is in the molecule, each hydrogen has, or let's say it this way, owns 1 valence electron. Does that make sense? Because for formal charge purposes, we split them back up. And so it's a neutral atom is supposed to have 1 valence electron. In the molecule, each hydrogen atom has 1 valence electron, so the formal charge equals 0. All right, what about boron? Boron is in group 3. So it a neutral atom has 3 valence electrons. There are 3 bonds, so that's 6 electrons in bonds, and they count half. So we would do 1/2 of 6 electrons equals 3 electrons. Now, when you do it, I don't think you need to do it this way. What you're going to do is you're going to look at it and count. When you see a bonding pair, we'll count 1, 1, 2, 3. Boron has 3. It's supposed to have 3 when it's neutral. It has 3 in the molecule. Formal charge equals 0. And so that's why this molecule is perfectly fine being like that. And we didn't, for this one, didn't have enough valence electrons to do anything different anyway. So let's see. I think I was going to do BF3 as well, wasn't I? Okay, so let's, I guess I probably have room on this sheet of paper. No, don't try and save a piece of paper and then make a mess and not have enough room. So let's do BF3, okay? Go ahead and draw this one and draw the best Lewis structure you can and hand it in on your way out of the room. Put it on the table in the back of the room, maybe next year. So if everyone is good, wears their mask, and we get a vaccine. So BF3, draw that Lewis structure, pause the video, come back. All right, are you done here? Okay, let's count them up. Boron's in group 3, 3 valence electrons. Fluorine is in group 7, so it has 7. There's 3 of them, so that's 21. So we have 24 valence electrons, or 12 pairs. Now, no, in class, I wouldn't do it this fast, right? I'd pause down. So 12 pairs. Let's draw the Lewis structure. What did you draw? Well, you put boron in the middle. Fluorine's connected with a single bond. And then let's stick the lone pairs, stick the rest of the valence electrons around the outside and see what we get. All right, 12 pairs, we've used 3, so 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a total of 12. Now I already kind of gave it away. Well, boron's okay being electron deficient, but this is one Lewis structure, right? Where fluorine is following the octet rule, 2468, and boron is electron deficient, and we've used all the valence electrons. But what if we considered having one of these fluorines share a pair, right? Why not? We could draw another Lewis structure where this shares, and now boron has an octet as well. Let's draw that. Boron, and it wouldn't matter which one we choose. I'll do the one off to the side here. And still, same number of valence electrons, right? And now I've satisfied the octet. So this one is, the octet rule is satisfied for boron. Which one is the correct structure? We don't know. All right, well, let's assign formal charges. Okay, now because you can pause this and repeat it if it doesn't make sense, I'm just going to say it verbally and do the counting. But let's do the fluorines first, okay? So we're going to do the top structure and then the bottom structure. So fluorine is in group 7. Here's how we would count it. Lone pairs count 2, so 2, 4, 6. Bonding pairs count 1, so 7. So does that make sense that fluorine has a formal charge of 0? Okay. Same with this one because they're identical. What about the boron? Boron's in group 3. Bonding pairs count half. So we're going to count those as 1, 1, 2, 3. So boron is supposed to have 3. It has 3. So boron, the formal charge is 0. So this one has all formal charges of 0. What about this bottom one? Well, I'm going to actually write in the formal charges right on the atoms as we do it. And for some of the WebAssign Lewis structures, you'll have to do that as well. Actually, I think you have to show formal charges on almost all of them. You know what? I'll record a video where I show the ChemPad and drawing Lewis structures. Actually, it's not ChemPad. Sorry, Marvin Sketch. To help you with that when we get the homework assignment. But anyway, let's put the formal charges right on here. Well, this fluorine on top is supposed to have 7 because it's in group 7, 2, 4, 6, 7, right? So that has a formal charge of 0. Put a little 0 there so you can see that. This fluorine's in the same situation, right? 2, 4, 6, 7. So it has 0 formal charge. What about this fluorine? It's supposed to have 7. It owns 2, 4, 5, 6. Aha. Now, write down what you think the formal charge is then. It's supposed to have 7. It only has 6. So it makes sense that it's plus 1. So it's plus 1 formal charge. What about boron? Supposed to have 3. It has 1, 2, 3, 4. Because remember, bonding pairs count half. So we just count 1 when we do this. 1, 2, 3, 4. So boron has an extra 1. So that's a minus 1. All right. So in this structure, I'll write this out so there's no confusion. Boron has a formal charge, not a real charge, but a formal charge, keeping track of charge, of -1. Oops, I forgot I zoomed in. Fluorine has a formal charge of +1. Does that seem reasonable to you? Well, we wouldn't have any basis to go on, right, at this point. Let me make sure it's focused. But think about how much, maybe I'll focus that again. It's not focused. Hopefully you can read it, or you can pull out a periodic table. Think about, how do we know whether formal charges make sense in a molecule? Well, electronegativity tells us how much different atoms like different elements like electrons, right? Fluorine is the most electronegative element. Boron is way over here, a lot less electronegative. So we might question the structure. We might question whether we could have boron with a formal charge of -1 and fluorine formally with a charge of +1, right? That doesn't kind of go with what electronegativities tell us about which one would like to have. Here I am anthropomorphizing again. But does that kind of, hopefully that makes sense. I wish I could look into your eyes, right? Does that kind of make sense to you? The formal charges in this case don't seem to fit with what we know about the chemistry of boron and fluorine. Fluorine really, 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 really likes electrons, almost as much as I like ice cream, right? So can it really be +1 formally compared to boron that's, yeah, I'll take frozen yogurt or something. Anyway, bad analogy. But these are opposite of what you would expect in a molecule, those formal charges to be. They're flipped in terms of the polarity. And so we might question this structure. Now, it's important to understand that later we'll talk about resonance and things. So there's other considerations going on. I don't at this point know. Actually, I think I do. There's probably argument about which Lewis structure. Remember, here's what I should stress. I should probably write this down. I think it will. Good idea. The Lewis structure is not the molecule. Okay. The Lewis structure is not the molecule. It's a really useful, really handy tool for representing molecules, and we can get a lot from it. We can get the shapes, and we can kind of have a pretty good guess at the bonding, but we don't know until we actually do an experiment and find out, what's this bond length and all that. Even there's some weird things where the distribution of charge might be different than what it shows up. So anyway, that is Lewis structures. I will do a bunch more examples of Lewis structures as well for different things. So resonance structures and just more examples of doing formal charges, polyatomic ions. All right, thanks everyone.